Welcome to the Codex Militaria channel. My name is Matija, and today we will be talking about the Battleship Bismarck. Bismarck was a German battleship of the Second World War that almost everyone has heard of. The legend surrounding her was created on the basis of her fascinating first and only operation in the Atlantic. However, alongside such a well-known and important battleship, there are also numerous stories and controversies, as well as various explanations for the problems that led to her defeat. Was Bismarck the most powerful battleship ever built in Europe? Or was she from the outset an outdated and unsuccessful design? Was her sinking the result of sheer luck? Or did she never truly stand a chance against the Royal Navy? In this series of videos, I will attempt to answer these and many other questions. We will look at the overall strategic picture and how Germany even came to build such a battleship in the first place. We will analyze all of her technical characteristics, her armor, armament, machinery, and everything else. All of these characteristics will be compared with battleships of that era. Finally, in the following video, we will go through the entire Operation Rheinübung in detail, which for Bismarck represented both her baptism of fire and her explosive end. To begin, we must examine how the construction of such a grand battleship came to be. Germany, after the First World War, was heavily restricted in the number and size of ships she was allowed to build, in accordance with the Treaty of Versailles. The first serious warships that Germany built were the three Deutschland-class heavy cruisers, called pocket battleships by the British due to their powerful armament of 6 283mm or 11-inch guns. Construction of these ships began in 1920s during the Weimar Republic, and the last ship was completed in 1936. These ships were built in full compliance with the restrictions of the Versailles Treaty, at least on paper. This meant that for every newly built ship, the one old pre-dreadnought, older than 20 years, was retired, and that the displacement of new ships was not greater than 10,000 tons. On paper, the Deutschland-class cruisers complied with those restrictions, but in reality, well, their standard displacement was around 11,000 tons or more, even up to 15,000 under full load. A small side note, standard displacement is a displacement of a fully equipped ship without liquids such as water supplies for boilers and fuel, while full load is the figure we get when the ship is completely filled with all these supplies. That term is no longer used today. However, this excess was small enough that it was difficult to prove, and insignificant compared to the excesses later committed by the Italians and especially Japan, and to a lesser extent even the USA with their Lexington-class carriers. In order to counter the combination of firepower, speed, and armament of these new ships, France built two smaller battlecruisers of the Dunkerque class, with a displacement of 25,000 tons standard or 35,000 under full load, which in all their characteristics were a step ahead of the German ships. At that time, Germany viewed the French Navy as the navy with which a conflict was most likely. This was also the only one they could realistically win, given that the British Royal Navy was so large that it would have taken them decades to achieve parity, and that only on the condition that Great Britain did not build a single new warship. This was, of course, difficult to expect, and neither Hitler nor the German Navy planned or built a fleet ready to challenge the Royal Navy. There is one wise saying I have heard many times: naval strategy is a build strategy. It takes at least 6 months to build a destroyer, and it takes 3 to 5 years to build a battleship. Strategic planning of the Navy needed for victory in war must begin decades before the conflict itself. This is what we saw in the latter part of the 1930s, in the lead-up to the World War II. The new French ships created the need for Germany to respond to them, and this was done through the construction of two battlecruisers of the Scharnhorst class. Legally, Germany was no longer bound by the Treaty of Versailles, since in that same year, 1935, the Anglo-German Naval Agreement was signed, according to which the restrictions of the Versailles Treaty were lifted, and Germany was given the possibility to build a fleet up to 35% of the Royal Navy. In reality, this meant that Germany could build 183,000 tons of capital ships, or 5 ships of 35,000 tons. Construction began in 1935, which means that the design of the ships was started under the Weimar Republic, while construction began during Hitler's rule. These ships were 3 times larger than the Deutschland-class cruisers, with a displacement of 38,000 tons under full load, an armor belt of as much as 320mm or 12.6 inches, and 9 283mm or 11-inch guns. These guns were of a new design, with longer barrels, heavier shells, and greater range than the guns of the Deutschland-class cruisers. Perhaps the most important characteristics of the new ship was their high speed of 31 knots. France now found itself facing a new challenge, to which it responding by building their Richelieu-class battleships. These battleships were in part a response to the Scharnhorst class and in part to the Italian Littoria-class battleships. The next German ships were the ships we are talking about today, two battleships of the Bismarck class. They were built as a response to the French battleships, and as a part of Hitler's aspiration to produce the largest and most powerful battleships in the world, which would be a symbol of the power of the Third Reich. The first ship was called Bismarck, and the second, Tirpitz. Their keels were laid in 1936, a year after the construction of the Scharnhorst has begun. They entered service in 1940 and 41 respectively, full 5 and 6 years after the building started. This class of battleships was originally conceived as an upgrade of the Scharnhorst with 330mm or 13-inch guns. It was subsequently decided that the design would be significantly modified and that 381mm or 15-inch guns would be installed, which necessitated a significant increase in dimensions and an altered design, although the similarities between the two classes were still significant. These guns were a response to the French and Italian ships, which had escalated gun caliber to that size. Officially, the new ships were built with the restrictions of 35,000 tons in accordance with the Second London Naval Treaty, but in reality, the standard displacement was 42,000 tons and under full load as much as 50,000. This makes Bismarck the largest battleship ever built in Europe, except for Vanguard, which was slightly larger, but also slightly too late to see service in the Second World War. As for the operational role for which the ships were built, there was a certain confusion. On the one hand, the German Navy with Admiral Raeder wanted ships suitable for attacking British convoys. This presupposed great range and speed, since that role assumes that the ships will flee from a stronger or equal opponent. The Scharnhorst-class ships are interesting in this regard since they are fast, of moderately large range, excellently armored, but the compromise was made in the weaker armament. On the other hand, Hitler wanted a battleship that would be the pride of Germany, capable of defeating any other battleship in one-on-one combat. These two desires resulted in a compromise, a ship that attempted to fulfill all these wishes, which it largely succeeded in doing, although the price of this had to be paid somewhere. And it was paid in its size and thus enormous cost, both financial and in required materials and amount of labor. We will go into details later, but for now it is sufficient to know that for the tonnage of two Bismarcks, 3 Scharnhorsts could have been built, or, if you look at the American, Italian or British Navy, 3 equivalent modern battleships. But more on that later. It is time to look at the basic characteristics of these ships. Official standard displacement was 35,560 tons, while true standard displacement was 42,243 tons. Displacement for Bismarck under full load was 50,955 tons, and even more for Tirpitz. The length of the ship was 241.55 meters, beam was 36 meters, while draft was 9.33 meters. Propulsion was provided by 12 boilers in 6 rooms through 3 sets of propulsion turbines. The total power installed was 138,000 horsepower, which allowed for a maximum speed of 30 knots. At 19 knots, the range was 15,788 kilometers, which means spending the full load of 7,461 metric tons of fuel. Crew was 2,065 people, out of which 103 were officers and 1,962 were sailors. Bismarck in Operation Rheinübung had 2,200 on board due to the additional crews for captured ships, while Tirpitz in 1944 had a crew of 2,500 due to the increased number of anti-aircraft guns, which required a large number of additional crew to service them. The main battery had 8 guns of 381mm or 15-inch in 4 turrets of 2 guns each. Secondary battery consisted of 12 guns of 150mm or 6-inch guns in the 6x2 configuration. Tertiary or heavy anti-aircraft battery was provided by 16 105mm or 4.1-inch guns in the 8x2 configuration. Medium anti-aircraft battery was 16 37mm guns, again in the 8x2 configuration. Light anti-aircraft battery was 18 20mm guns in single mountings, and finally, the armor had a main belt of 320mm or 12.6 inches, and the armor scheme will be described in more details in a future chapter. The 381mm guns with the designation SKC/34 were guns of a completely new design and had no similarities with the older weapons with which the Bayern-class ships were armed in World War I. It is interesting to mention that it was also planned for the Scharnhorst-class ships to be upgraded to that gun caliber through 3 gun turrets with 2 guns each, thus a total of 6 guns. At the time of their construction, the new guns were only in development, and Hitler did not want to provoke Great Britain at that time by escalating the caliber. Namely, according to the Second London Naval Treaty, which was negotiated in 1935 and signed in 1936, all signatories were limited to a gun caliber of 14 inches or 356mm. German construction of ships with guns of larger caliber would certainly provoke a counter-reaction from the signatories and escalation in all states. It was considered wiser to agree to a lower caliber so that the other states would not increase it. In the end, this only had an effect on the King George V class battleships for the Royal Navy, while the other signatories built battleships with gun calibers of 381 or 406mm, 15 or 16 inches. The escalation of allowed caliber of guns under the agreement happened in 1937, early enough for the change of guns on American battleships, but too late for the British. This meant that the Bismarck-class battleships began construction before that escalation clause came into force, which shows a clear willingness on Germany's part not to respect that agreement to which it was a signatory. But when the clause came into force the following year, it was irrelevant anyways. The new German guns were designed with very long barrels in order to achieve greater shell velocity, which results in greater range, armor penetration, and a flatter shell trajectory, which increases accuracy. The guns had a barrel length of 51.66 calibers. For comparison, the guns of the Bayern-class battleships of the same caliber as Bismarck's had barrel length of 45 calibers, and British battleships 42 calibers. The shell was heavier than Bayern's, 800 kg for Bismarck versus 750 kg for Bayern, but lighter than British ships whose shell weighed 879 kg. The lower weight of the shell favorably affected its muzzle velocity, which was an advantage at shorter ranges, but it retained penetrating power less well at greater ranges. The high velocity also enabled a flatter trajectory and therefore greater accuracy, although at long ranges it was a disadvantage due to the smaller ballistic arc over which it was possible to penetrate the enemy deck with plunging fire. The price that had to be paid for these more favorable characteristics was in barrel life. They were designed to withstand about 180 to 200 firings, unlike British guns which could withstand 330. The powder charge amounted to 212 kilograms of propellant, divided into a 4-charge in a silk bag of 99.5 kilograms and a main charge in a brass case of 112.5 kilograms. The brass case is a peculiarity of the German gun industry, unlike other navies which use ordinary silk bags, as we see in this example from the battleship Iowa. Brass was used because that metal does not spark when it comes into contact with other metals, and the case itself weighed 70 kilograms. It was ejected onto the deck after use. The powder charge was not ordinary but slow-burning explosive. 1/100th of a second was needed for the charge to burn. However, that 100th is what makes the difference between giving the necessary thrust to the shell and an ordinary explosion that would destroy the barrel, gun turret, and probably the rest of the ship. In the next video, we can see what the typical preparation for firing looked like on the British Queen Elizabeth class battleship. In principle, things are very similar on Bismarck as well. The propellant and powder charges would come from the ammunition magazines located below the turret via hoists. And on the way, there were several armored doors to reduce the chance that in the event of a hit on the gun turret or in its vicinity, flame would penetrate into the ammunition magazine, since there is not yet a battleship that has survived this. Something like this happened to the British battlecruisers in the Battle of Jutland. But that is a story for another video. We see that the gun is loaded when it is almost horizontal. This was the only way to load guns of this caliber due to the enormous weight of the ammunition. In case of failure of the automatic loader, it was possible to load the guns manually, but this required the work of 10 to 14 crew members, and it was truly a desperate move. The rate of fire was officially 2.3 to 3 shells per minute, but this is an optimistic figure under ideal conditions and at zero elevation. In actual battle, few warships, and Bismarck as well, exceeded the rate of fire of 1 shell per minute per gun. The literature says that between 112 and 130 shells were carried per gun barrel. The higher figures certainly include up to 5 ready shells that were located in the gun turrets. One interesting question is why the Germans decided to mount these guns in 4 turrets with 2 guns each, when all battleships built between the 2 world wars used turrets with 3 or even 4 guns. Turrets with 3 guns made it possible to save on weight while gaining in number of guns. For example, Nelson carried 9 guns in 3 turrets, while Bismarck carried 8 guns, 1 fewer, in 4 turrets. The answer is not clearly given from the German side, but we must consider that there were advantages and limitations of these approaches. The Germans built the Deutschland and Scharnhorst classes with turrets with 3 guns, so they certainly knew how to construct them and what were their advantages. However, a larger number of twin turrets meant that firepower was equally distributed fore and aft. This enables better distribution of fire through alternating half salvos of 4 shots to determine distance to target more quickly, and also better distribution of fire if 2 targets are being engaged, by dividing into forward and aft gun turrets, with their respective directors. Perhaps the main advantage is that this system makes the main armament more resistant to damage. Namely, a hit on 1 turret in a system with triple turrets would knock out 33% of firepower from the battle, while in a system with 4 twin turrets, only 25% of firepower would be out of action. Twin turrets are more accurate due to the greater spacing between guns, which do not interfere with each other with exhaust gases from the barrels, which can increase dispersion. This was a problem on a large number of ships, and especially American battleships built at the end of the First World War, or for example on Italian Zara-class cruisers. As we can see in the attached image, the guns are placed too close to one another and thus interfere with each other in firing. Compare that with Bismarck, on which there is a large spacing between the guns, thanks to which this problem does not exist. Incidentally, the way such problems were solved was not to fire the guns simultaneously, but with a small time delay of a fraction of a second. Of course, this solution brought with it the problem of added inaccuracy, but in principle the advantages were greater than the harm. An additional reason for turrets with 2 guns was the way the Germans constructed their guns. Namely, they used their system of horizontal sliding breech block, which in theory was faster for loading the gun, and could be used thanks to the brass cases which helped in better sealing of the gun. This system was perfectly functional, but required additional horizontal space, which would create problems in turrets with 3 guns. Finally, Bismarck was designed and built with a large number of backup systems. Thus, unlike basically all other navies, it had backup loaders and ammunition hoists in the gun turret. This created the need for a wider and larger turret. As we see in the attached image, Bismarck's gun turret is significantly larger than that on the British battlecruiser Hood. Had it been designed for 3 guns, the turret would have been even larger and heavier, and possibly too large for the hull the Germans wanted. At the bottom we see the enormous turret of the battleship Yamato with 460mm or 18-inch guns, for comparison. However, there is a price for everything, and so too for these advantages. It was paid through the additional weight of the additional gun turret, and the greater length of the hull that had to be armored. All of this significantly increased the ship's weight. The gun turrets on all German ships had names in alphabetical order: Anton, Bruno, Caesar, and Dora, or ABCD. Let us now look at the ballistic characteristics of these powerful guns at different ranges. The data provided are obtained from the original German graphs for armor-piercing ammunition, available on kbbismarck.com website, which are somewhat difficult to read, so I have adapted them into the table form. It should be kept in mind that this data does not give a definitive picture, but depends on a number of other factors. For example, this data is valid for armor that is positioned vertically, but ships rock on the waves, so the angle of impact varies. The quality of armor varied. After that, ships used to have multiple layers of armor, and these values do not add up linearly. The armor itself can be positioned at an angle, as was done on American battleships, where the angle was 12 degrees from vertical. In the part of the video that relates to armor, we will describe in more details how the angle of impact affects armor resistance and all other variations. In the next table, we can see a comparison with battleships built before or during World War II. Again, we have too much data to read it all, but we can make some general comparisons. Before we begin, I would note that these figures were obtained using the same methodology, that is, the empirical formula for armor penetration, and taken from the same source, the Battleships book series. If we compare them with data from national methodologies, we can get somewhat different results, so this is the only correct way to compare different guns. Also, due to the differences in yards and meters, some ranges are not identical, especially for Yamato, whose figures are for 2 or 3 kilometer greater distances. However, better data than this does not exist. We can see that the French Richelieu-class ships have guns with characteristics very similar to Bismarck, and only at greater range does the heavier shell give better results. The guns of Italian battleships have exceptional characteristics, if we briefly forget that in practice they had enormous problems with accuracy and durability. British battleships are not competitive, except at long range when they are better against deck armor. The Americans, with their 406mm or 16-inch guns, were a step ahead, but the difference is not large, especially below 20 kilometers. What makes the difference is the fact that the German guns had a flatter trajectory, which made them more accurate, but limited their ability to penetrate the thinner armor on the ship's deck. The greater the ballistic arc, the more perpendicularly the shell falls on the enemy ship at long range, and therefore there is an increased chance that the shell will penetrate the deck and explode under it. This is the type of combat for which the Americans built their battleships: long-range fire with super heavy shells that fall in a high arc onto the enemy's deck. The Germans went a different way. They optimized their guns for combat at shorter range, which they considered more probable in the fog and storms that characterized the North Atlantic. The flat trajectory and high velocity of the shells enabled easier penetration of the enemy's side armor under those conditions. The explosive charge of armor-piercing shells was 18.8 kilograms, and for high explosive shells with contact fuse it was 64.2 kilograms. Although this seems small since both shells weighed 800 kilograms, you must keep in mind that the shell had to withstand firing with the 200 kilograms or 400 pounds of powder charge while in the gun barrel, exit from it at a velocity of 820 meters per second or 2.5 Mach, withstand flight up to 35 kilometers, penetrate at least 30 centimeters of steel in the enemy ship, after all of that remain in one piece for another 0.035 seconds, and only then detonate. The fuse and explosive charge had to survive all these enormous forces, and that is the reason why the vast majority of the shell's weight was actually spent on keeping the shell in one piece and protecting the fuse and explosive charge, long enough for them to do their job. Since the task of penetrating enemy armor without the shell being flattened on that armor is an extremely difficult task, armor-piercing shells were built with thicker walls than contact high-explosive shells. Consequently, for this reason, they have a smaller explosive charge. Here I must point out that the German shells were far from perfect, since at least one remained unexploded during the battle in the Denmark Strait, buried in the hull of the battleship Prince of Wales. The analysis I have read on this subject point to the conclusion that the German fuses were of simpler and less reliable construction than, for example, the American ones. While we are on the subject of shell construction, we can also deal with that aspect. All large-caliber armor-piercing shells had 3 basic parts: the shell itself, the armor cap, and the windscreen. In the next image, we can see what this looked like for American 406mm or 16-inch shells in the First World War. On the left, we see the shell itself, in the middle, the armor cap, and on the right, the entire shell together with the windscreen at the top, which had only an aerodynamic purpose. That is, it had no function upon impact. In the next image, we can see an unexploded shell from the battleship Warspite, next to which is also the armor cap that fell off the top of the shell. Armor caps were not an integral part of the shell, but upon impact with sufficient thickness of armor, they would fall off the top of the shell. Their purpose was to protect the penetrator, which is the tip of the shell, in case of the armor being targeted was so hard or thick that it would withstand the impact of the shell without the armor cap. The armor cap transfers the force of impact from the point at the top of the shell to the entire circle around its tip, and thus protects it from disintegration. Also, they open a hole in the enemy armor through which the rest of the shell can then pass through. In this way, armor caps helped with hits that were not at right angles, because they helped prevent the shell from bouncing off the armor, which along with deformation was the main way armor worked. This is perhaps easiest to imagine as when you pre-drill the wood a little before you start inserting a screw, to be sure it won't slip. Armor caps were extremely hard, weighing about 100 kilograms, and were relatively expensive to manufacture. Modern armor-piercing gun ammunition has largely gone in the direction of subcaliber penetrators, which, however, are not suitable anti-ship weapons, since they do not have an explosive charge that would cause damage inside the ship after penetration of the armor. Bismarck itself, as we said, carried about 125 shells per gun, or a total of about 1,000 heavy shells. Of these, 1/3 were armor-piercing shells, 1/3 high-explosive shells with armor-piercing caps, and 1/3 contact high-explosive shells without the armor-piercing cap. All shells, except contact ones, were equipped with a fuse at the bottom of the shell that delayed the explosion 0.035 seconds, or 35 thousandths of a second. High-explosive shells with armor-piercing cap were intended for action against less armored targets, such as cruisers, where the armor cap helped them penetrate armor that was rarely thicker than 100 mm. Armor-piercing shells were intended for action against other battleships, and high-explosive shells were used against all other targets, such as destroyers and merchant ships. At the end of this chapter, we can conclude that the Bismarck-class ships had an excellent main battery. It was primarily intended for close combat, below 20 kilometers, where it had excellent characteristics for armor penetration, accuracy, and rate of fire. At greater ranges, other navies, especially the American, tended to use armament that would drop a heavier shell in a greater arc onto the deck of the enemy ship, which was considered an easier target than the armor belt. But given the weather conditions that typically prevailed in the Atlantic, and the conditions of typical combat in which the range would quickly decrease after the first salvos, it's hard to fault Germany for making the decisions to go in this direction of main battery development for its guns. Bismarck, with its main armament, was a dangerous foe for any battleship it could encounter. The great stumbling block in the Bismarck class was a split secondary battery, which consisted of 150mm or 6-inch guns, intended exclusively for action against naval targets, and an anti-aircraft battery of 105mm or 4.1-inch guns. The tendency of that era was to unite these batteries into dual-purpose guns that could perform both these roles in one weapon. The most successful example of this is the American 5-inch 38 gun, or 127mm, which was very useful in both roles. However, this necessarily means a compromise in each of these areas, and the German designers would not accept it. Namely, when engaging surface targets, range and explosive force are very important, while for anti-aircraft guns, the most important characteristics are high elevation and rate of fire, in order to create an effective barrage which would deter or destroy aircraft. The problem is that the guns of this era were loaded manually, since automatically loaded guns only appeared near the end of the war. The 127mm shell weighed about 25 kilograms, which was considered a practical maximum for fast manual loading. Although one person can potentially lift even a heavier shell, in combat that lasts several minutes, or even hours, this is not practical due to fatigue, which then affects the rate of fire. For this reason, most navies used this or a smaller caliber for their secondary batteries, although the weight of the shell itself meant that one hit would probably not inflict major damage, even on an unarmored ship. This would be compensated for by the rate of fire, and dual-purpose weapons were justified by the savings in weight due to fewer guns, ammunition, and crew members who had to operate these weapons. The Germans, however, did not want compromises. The 150mm gun they already had was a very effective anti-ship weapon, but due to the shell weight of 45 kilograms, it was limited to a rate of fire of 8 shells per minute. The Germans wanted to retain the long range and destructive power of this weapon, so they installed 12 of them on Bismarck, in 6 twin gun turrets, 3 on each side. By comparison with the already mentioned American gun, we can see that there really are a number of valid reasons for retaining this gun. Compared to the American weapon, the German gun had 8 kilometers greater range, almost twice as heavy shell, and a high velocity which improved its accuracy, although it loses in the rate of fire, 8 instead of 15 shells per minute. The maximum elevation this gun achieved was 40 degrees, which means it could not be effectively used against aircraft. For this to be achieved, the gun turrets would have to be significantly larger. Don't forget that usually 2/3 of the gun protrudes from the turret and the remaining third is inside it. This means that the gun turret must be high enough for the rear third of the gun to be able to stand almost vertically inside of it, which is necessary for the gun to be able to function as an anti-aircraft weapon. With a barrel 8.25 meters long and weighing 9 tons, this was simply not practical. This is another reason why there are practically no dual-purpose guns of this caliber. The German 128mm anti-aircraft gun, with comparable or better properties than American or British guns, had not yet been developed at this stage of the war. It must be mentioned that Tirpitz's secondary guns were modified to be elevated more in 1944, but no such modifications were made for Bismarck. If we must summarize and consider what is the main reason for using this gun, it is probably the destructive power and range of the 150mm shell. This caliber enabled Bismarck to severely damage a destroyer or even an average cruiser with just one hit, while the effect of a lighter shell would be significantly lesser. Or, in the case of targeting a cruiser, there might not even be any, since cruisers were generally armored to withstand hits from medium caliber guns in their critical parts. The tertiary battery consisted of 105mm guns, of which there were 16, 8 of each side of the ship in 4 twin mounts. These guns had a maximum range of 18 kilometers and could fire 18 shells per minute. Each shell weighed 15 kilograms or 30 pounds. Their maximum elevation was 80 degrees. In terms of performance, this was a classic, decent anti-aircraft gun for its time. Weight savings were achieved through the fact that these guns were not in armored gun turrets, but rather in open mounts, as we can see in the image below. This reduced weight, but made them more vulnerable to damage. This would become obvious when Tirpitz was attacked by British bombers in Norway, when losses among the crew were horrific under concentrated air attack. The advantages of this system was that the two types of guns were truly better, each for its task, rather than the dual-purpose weapons. The 150mm guns had greater range and destructive power of each shell, while the 105mm guns had significantly higher rate of fire, which is important in shooting down aircraft. Such a system enabled firing against naval and air targets at the same time. German planners considered this a possible situation, and the divided battery enabled the ship to defend against these targets simultaneously, which wasn't as easy with dual-purpose guns. Also, ships of other nations could count on being surrounded by a fleet of smaller ships that would fight against other smaller ships, while the task of their capital ships was to fight against other capital ships. German ships in the Atlantic would certainly not be in such a position, but would be alone against a larger enemy fleet that included aircraft as well. In that situation, all additional firepower could help with the ship's survival. Therefore, we can conclude that the Bismarck's divided secondary battery was not necessarily a problem and had some advantages over a unified dual-purpose battery. But we must also look at what its disadvantages were. The additional weight high on the ship's superstructure meant that the ship had to be larger to remain stable, as the ship had to carry additional fire control equipment, and more crew was needed for ultimately the same firepower as smaller battleships of other countries. If we compare the weight of fire with, for example, American battleships, which had 10 127mm 5-inch guns on each side, then we see that they can fire 3,750 kilograms of shells per minute, while Bismarck, with both batteries combined, fires 3,960 kilograms from 16 barrels. However, against aircraft, this falls to only 1,800 kilograms. Which gives American ships with only 10 gun barrels a double advantage over 16 German ones. For this reason, the German divided secondary battery is definitely inefficient in terms of space, weight, and complexity, due to the need for two different fire control systems for two different gun calibers. Thus, the divided battery had its advantages and disadvantages, as with mostly everything. The Germans knew very well what the modern trends were and had several different options they could have chosen instead of the solution with two separate batteries. German destroyers were armed with an excellent 128mm gun that was installed on them from 1934. If they had wanted, they certainly could have adapted it for anti-aircraft purposes and thus obtained a unified battery that could be effective in both purposes. In this way, the total number of guns and thus the weight on the superstructure could be reduced while not losing almost anything in firepower both against aircraft and against naval targets. Or they could have standardized all guns to the same caliber of 105mm and thus maintain the same number of barrels, which could now be more easily directed and concentrated on one target. But that was not the German style. If you follow the development of their weapons during Second World War, then it is clear that they always wanted to have the ideal tool for every situation without compromise. The medium anti-aircraft battery consisted of 16 37mm SKC/30 guns. These guns were among the worst anti-aircraft guns in the war. Although they had long range and accuracy compared to comparable weapons, they were semi-automatic, which meant that each shell was loaded individually by hand. This reduced the rate of fire to a maximum of 30 shells per minute. The 40mm Bofors, standard armament on American ships, had a rate of fire of 120 shells per minute. This German gun was more similar to a sniper rifle, a weapon of great power and accuracy. In practice, this approach proved to be a failure, and later German 37mm guns were capable of automatic fire, which made them significantly more effective. These guns had a maximum range of 8.5 kilometers and a firing ceiling of 6.8 kilometers. The effective range depended on the altitude at which the targeted aircraft was approaching, but usually this was below 5 kilometers. These guns were stabilized in 3 dimensions, but the system was not reliable and on later ships was even completely removed. Finally, Bismarck also carried 16 guns of 20mm for close-range anti-aircraft fire. These weapons were comparable with similar weapons among the Allies, for example the 20mm Oerlikon. The maximum range was about 5.5 km and the effective one about 2.5 km, again depending on the altitude of the targeted aircraft. Now let's talk about the equipment that enables Bismarck to find and hit its targets. Fire was controlled from command centers. For the main and secondary batteries, there were 3 such facilities on the ship. The central and aft command center were equipped with stereoscopic rangefinders 10.5 meters wide, while the forward fire control center had a 7-meter rangefinder. The central command center was considered the main one, where the first gunnery officer was located. He had a rangefinder with a magnification factor of 50 times, and his command position could rotate 360 degrees. The forward and aft command center couldn't rotate fully because of the ship's superstructure. Stereoscopic rangefinders functioned in such a way that from each end the image was sent by mirrors to the center. The exact angle was adjusted until the 2 images from the 2 ends of the rangefinder overlapped into one. Since it was known which angle corresponds to which distance, in this way the exact distance of the observed object could be determined. The larger the rangefinder, that is, the greater the spacing between the mirrors at the end of the rangefinder, the more accurate the rangefinder is, because it is possible to measure the angle of the mirrors toward the target more precisely. Inside the ship, in the plotting rooms or Rechenstellen, were the fire control computers, which were used to calculate the exact elevation and direction of the guns. The computer had a designation C/38K and was a highly advanced piece of naval technology for the time. There were 2 separate plotting rooms in the ship, and they could be rewired to serve information to the main or secondary battery as needed. C/38K was an analog electromechanical computer, which took data such as range, bearing, speed, on-ship's movement, wind, and other ballistic factors, and would provide a firing solution. Operators would feed in data from rangefinders and radar, and C/38K would continuously update the gun-laying order to keep the weapons on target. All command centers were connected by cables to the gun turrets, which they thus controlled remotely. There is a myth that these cables were unarmored and that this was a significant design flaw. However, this is not completely true. The cables ran below the main armor to the guns, and to the command centers in superstructure, they ran through armor tubes. However, since the main command center was located 31 meters above sea level, its cables were poorly armored, especially near the top. The great weight of armor so high on the superstructure would negatively affect the ship's stability. If necessary, that is, if the main command center was destroyed or cut off, other centers would take over fire control. If all three command centers were knocked out, all main gun turrets, except Anton, had local fire control through a 10.5 meter rangefinder. Anton also had it when the ship was first built, but it was removed after the first trials because it was damaged by the sea surging over the bow. Interestingly, in several places I have read that it was precisely that rangefinder that was sold to the Soviet Union, for which Germany was building one Admiral Hipper-class cruiser and was helping with other naval equipment. Local fire control from the turrets was significantly less effective due to the significantly lower position at which it was located, which made visibility difficult and made its use practical only at short range. The central 150mm gun turret on each side also had its own 6.5 meter rangefinder. After visual determination of range, fire would typically be opened from 3 gun turrets in partial salvos so that 6 shells would be in the air simultaneously. First pair a little in front, second exactly on target as visually determined, and the third behind the target. The aiming distance between pairs of shells was around 400 meters. The fall of the shells would be tracked and fire would be corrected according to the results. This was not a particularly fast method because, as we saw earlier, at maximum range, shells flew over a minute to the target. However, German optical equipment was of quite high quality and the crew very well trained, so it was quite possible to achieve accurate hits already with the third salvo, as was shown in practice. Anti-aircraft fire was controlled by 4 command posts, 2 of which were located on the main part of the superstructure in spherical cupolas, and 2 at exposed positions on the aft part of the superstructure. All 4 were equipped with 4-meter rangefinders. These command centers primarily directed the fire of the tertiary battery of 105mm guns. 2 additional 3-meter rangefinders existed on the command bridge, and smaller rangefinders locally helped in directing the fire of medium and light anti-aircraft guns. As for other sensors, Bismarck also possessed radar. These were 3 sets of FUMO 23 radars, which were located immediately above the 3 main fire control centers and could rotate together with them. The maximum range was 25 kilometers, but since these were not particularly advanced devices, the information obtained was not precise enough to direct fire with them. They were used for helping to determine distance to target, but they were not wired to the fire control computers. Therefore, the results had to be put manually in the computers. The display was on a screen using an oscilloscope, so it was not possible to track more than one target, and even the distance was not easy to read precisely. The Allies already had more advanced systems which they were installing on their ships in increasing numbers. So for example, the new British King George V class battleship had separate radar for detecting aircraft and radars for fire control. However, these radars in good weather were not significantly more accurate than optical systems. For example, the German Z-Takt at 20 kilometers could determine distance with an accuracy of 100 meters. However, top-quality German optics in large rangefinders, manufactured by Carl Zeiss, in ideal weather could achieve accuracy of 200 meters regularly, and in excellent weather even up to 50 meters at those distances, which is the reason why the German Navy in this period relied primarily on optical instruments. Later in the war, radar would prove irreplaceable in warfare at night and in poor weather conditions, which Scharnhorst particularly felt at the Battle of North Cape. The installation of radar was also not simple, because it required that the fragile and heavy antenna, and almost always several of them, be placed at the highest possible point on the ship, and that the necessary cables, electricity, and monitoring spaces be secured, which added weight to the top of the ship and negatively affected its stability. Also, we must keep in mind that in development of radar, German focus was on aviation, while the Navy, due to the small number of ships and strategic influence, was somewhat secondary and only later received the newest radars. Although it will sound unusual, in some conditions a more useful sensor was a hydrophone. There were 2 sets of 60 microphones positioned on each side of the ship, which depending on conditions could detect the noise of enemy ships at distances of as much as 40 kilometers and precisely determine the direction from which they were coming. During the battle in the Denmark Strait, using such hydrophones, the cruiser Prince Eugen detected British battleships before it found them by radar and visually. On the other hand, the cruiser Suffolk got a reading from radar that Prince Eugen was at 19 kilometers and opened fire, while in reality the distance was 27 kilometers. In the end, we see that Bismarck was equipped with sensors in accordance with the time in which it was created. Its optical instruments were perhaps the best in the world, and the electronics were decent, although they lagged somewhat behind what the British and Americans had. However, this difference did not come to the fore in its short career, but would only be a problem in later years of the war when the difference in radar quality shifted more significantly to the side of the Allies. The Bismarck-class ships were heavily armored. At the same time, their armor is an enormous stumbling block, and the reason why numerous historians and naval engineers declare it outdated for the period of history. Who's right? Well, time to find out. Bismarck had 19,000 tons of armor, or about 40% of total weight. This is by far the largest proportion among any battleship. Yamato had about 23,000 tons, which was greater, but in percentage, this was about 33% of its total weight, and that was approximately the standard among battleships of that era. Was Bismarck then better armored and protected than its competitors? Well, the answer is both yes and no, as we will soon see. First, we must talk about the important concept in battleship armor, which appeared between the two world wars. This is the all-or-nothing principle. Namely, some parts of a warship are more important than others. These are primarily its propulsion machinery, which move the ship, and without which it is immobile, an easy target incapable of returning fire, because even the electricity needed for the functioning of communications, sensors, and other weapon systems comes from those engines. Therefore, the machinery, that is, boilers and turbines, are located deep in the middle of the ship, where they are best protected. The drive to the propellers comes through enormous shafts that run through the central and aft part of the ship. These shafts are heavy and produce a lot of noise and vibrations, but are necessary to ensure that the engines are protected in the middle of the ship, instead of at the vulnerable stern. The propellers, rudders, and motors for turning the rudders are also very important, but it is almost impossible to fully protect them. We'll talk more about this issue later. The second crucial part are the ammunition magazines. And I don't think I need to specifically describe why this part is crucial. It is enough to look at the British battlecruisers in the Battle of Jutland, although that is a somewhat more complex story that I will tell in the future. Suffice it to say that 3 British capital ships exploded and sank almost with all crew members as a result of ammunition explosion. These magazines are also in the middle of the ship, usually below the gun turrets, which are typically located immediately in front of and behind the engine rooms, and are heavily armored. Finally, the guns are located in armored turrets, which are connected to the ammunition magazines by thick armored tubes called barbettes. As we can see, it is of the utmost importance to protect the middle of the ship, and this central protected part is typically called the citadel. The citadel would have to be spacious enough to fit everything necessary for the ship to function as a combat unit, and which should ensure that the ship does not sink even if the rest of the ship is completely shot up. The larger the citadel, the more armor is needed to protect it, which increases the weight of the ship, which requires a larger hull and more machinery to maintain speed, etc., etc. Additionally, weight was important because of the 35,000-ton limitation imposed through various naval treaties. Different nations tried in various ways to reduce the area that needed to be armored. The British Nelson and French Richelieu-class battleships concentrated all heavy armament forward of the superstructure in order to reduce the citadel and save on weight. Between the wars, high-pressure boilers were developed which enabled greater power to be obtained from less weight of the machinery. Together with these innovations, the way armor was distributed across the ship also changed. Namely, the armor scheme used in the First World War is today called the distributed armor system, which means that although the citadel was the best protected part of the ship, a certain weight of armor was distributed, so that other parts would also be protected, such as the superstructure, bow and stern, as well as the upper part of the hull. Thus, battleships had areas protected with heavy, medium and light armor. In contrast to this, The American battleship Nevada, which began construction in 1911, was the first battleship to use the new system called all or nothing. The idea was to put the heaviest possible armor over the critical parts of the ship, while the rest was practically unarmored. This system gave the greatest possible protection to the machinery, ammunition, and guns, while the bow, stern, superstructure, and sometimes the upper part of the hull were unprotected. But as long as the citadel was not penetrated, the ship in theory should not sink. Since all battleships built after the First World War, except perhaps the Italian Littoria class, were built with the all-or-nothing system, it is interesting that Bismarck designers went along a different path. Before I describe in detail how Bismarck was protected, I would just mention that this design is not the result of ignorance or simply reusing old blueprints. Bismarck's designers knew perfectly well what the modern trends were and what their advantages and disadvantages were. Also, there was no obstacle in terms of knowledge or capability in shipbuilding. The system they chose was in accordance with their vision of the type of tasks and environment in which these ships would potentially find themselves. But it is also impossible not to notice similarities in armor design with the last class of German battleships in the First World War, the Bayern class. The reason for this is very simple. In the Battle of Jutland, German ships withstood a horrifying number of hits, and this gave German designers reason to think that they were on the right path and that nothing needed to be changed. For example, the battlecruiser Seydlitz was hit with over 20 heavy shells and 1 torpedo, and despite this sailed back to Germany independently, although its bow was almost at sea level when it came to port. Therefore, German designers made a conscious decision to retain the good aspects of this armor and upgrade it in accordance with modern threats, which would be long-range fire and aircraft. Let us now look at how Bismarck was specifically armored. The main armor belt was made of 320 mm or 12.6 inches of steel with a length of 170 m and height of 4.8 m. This belt covers 70% of the length of the hull, which is again a record among battleships. The armor belt was mounted externally on the hull. The new British ships used a similar technique, while American, Italian, and French battleships mounted the armor belt inside the hull, in order to enable it to be at an angle of 12 degrees. Yamato, on the other hand, had the armor belt at an angle, but on the outside of the hull. Placing the belt at an angle was a solution that increased the angle at which shell hits the ship, and therefore increases the effective thickness that the shell must penetrate, especially at long ranges, where the angle of the armor adds to the angle of fall of the shell. Also, the outer layer on the ship's hull can be a thinner armor plate that cannot stop a heavy projectile, but can potentially disrupt its armor cap, and thus reduce its potential to penetrate the main armor belt. Italian Littoria class battleships were directly designed in this way, with external armor of 70 mm that was considered sufficient to disrupt the armor cap on heavy shells, and thus give the main armor belt of 280 mm a better chance to withstand a hit. However, an internal armor belt means that a larger volume of the hull needs to be spent on it, which limits the useful space that the armor belt protects. Also, since the belt was at an angle, in case of a hit, the outer layer would be damaged or destroyed, which created a problem due to flooding that was possible between the internal armor belt and the external hull of the ship. Since the outer layer typically could not withstand a hit even by smaller projectiles, that meant that, although the main part of the ship was protected, it was possible to receive damage that could not be repaired during sailing, and which, due to the flooding, would slow the ship and impair its stability. For this reason, German and British designers chose a vertical belt on the external part of the hull, whereby these ships were completely immune to small and medium projectiles, with savings in weight due to greater useful volume inside the hull, but also with the aforementioned disadvantages, which were considered acceptable. Due to the narrowing of the hull towards the bow and stern, the belt at those parts was nevertheless angled. At turret Anton, 17 degrees, Bruno 10 degrees, Caesar 7 degrees, and Dora 8 to 10 degrees. This can perhaps best be seen in the next image, where it is clearly visible how the main armor belt, lower part of the hull, curves as we go from the middle towards the bow of the ship. However, that's not all. There's more. The Scharnhorst and Bismarck-class ships had so-called turtleback armor, that is, the main armor deck. This means that below the upper deck and behind the main armor belt, there is an additional armor belt and deck. As we see in the image, it connected the main armor deck of 80mm or 3.1 inches with the lower part of the armor belt, using an armor plate positioned at an angle of 22 degrees from horizontal. This angled plate was 100mm or 4 inches thick above the machinery and 120mm or 4.7 inches above the ammunition magazines. This internal armor was the key to Bismarck's armor scheme. It ensured that practically no projectile could penetrate both armor plates and enter the citadel. Namely, the angle at which the armor is hit determines what is the real thickness that the shell must penetrate. The effect of this slope is small, up to approximately 30 degrees from horizontal, when it sharply increases. Let us take a concrete example and see what happens if we enter this data into the calculator from the panzerwheel.net site. We mentioned that Bismarck's belt curves around the bow and its slope is 10 degrees at turret Bruno. If we enter that into the relative armor thickness calculator, and if we assume that the projectile comes completely horizontally, then we see that the effective thickness of armor that the shell must penetrate is about 325mm instead of 320. However, if we assume that the incoming shell is falling at an angle of 10 degrees, then we get an effective armor thickness of 330mm. Let us see what happens if we take into account the angle of 17 degrees at turret Anton. Now we have obtained 340mm or an increase of 6%. This is not significant, but it is not negligible either. And now, the main reason why we are examining this hypothesis. Let us see what happens if a shell arrives horizontally through the main armor belt. The 120mm armored plate at this angle becomes 266mm of effective armor, and that is after the shell had to penetrate the main belt of 320mm. Together, this creates a barrier of 586mm or 23 inches of armor in 2 layers. Even at very close range, such armor was difficult or impossible to penetrate. Of course, shells rarely arrive perfectly horizontally, but always at a certain angle. But as the angle increases and the internal plate loses effective thickness, the main armor belt increases in effective thickness, especially around the gun turrets. Nevertheless, that is not all the armor on Bismarck. Above the main armor belt was the upper armor belt of 145mm of steel. This armor could be considered medium armor, since it provides good protection from light and medium guns, but will not stop any heavy projectile. That armor plate is actually the main difference between the armor on the Scharnhorst and Bismarck classes, whose armor is otherwise very comparable in arrangement and thickness. The front side of the citadel was closed by an armor plate that was 220mm or 8.6 inches thick at the top, 180mm in the middle of the ship, and 145mm at the bottom. At the bow and stern, at the waterline, there were 2 additional armor plates. At the bow it was 60mm and at the stern 80mm. No ship of that time had armor plates at the bow, but for the Germans there was a historical reason. The battlecruiser Lützow at Jutland had its bow damaged by 381mm shell that was a key factor in its sinking after the battle. The Germans did not want this to happen again, at least not with the lighter shells. As for the horizontal armor, the deck was armored with 50mm of armor, which was increased to 80mm above the ammunition magazines. Below it was a bulkhead with 6 to 20mm of armor made of softer steel, and below it is the main armor deck of thickness from 80 to 100mm, again above the ammunition magazines. The bow was unarmored, and the stern had an extension of the main plate with a thickness of 110mm. The stern is additionally armored compared to the bow because of the motors for turning the rudder, which were located there. In this way, the effective thickness of horizontal armor against bombs or projectiles from extreme range that would fall perpendicularly on the deck was between 130 and 200mm, 5.1 to 7.8 inches, depending on the part of the ship being observed. The true thickness of armor naturally varies depending on the angle at which the projectile falls on the deck. Although we cannot say that this is a poorly armored part of the ship, when we compare this armor with decks of 150mm on the British King George V class, or 170mm on the Richelieu class, plus the internal layers that these ships had, then we see that the horizontal protection, important against aircraft and for long-range combat, was its weakness. To draw correct conclusions, we must become familiar with three more phenomena that are important in understanding how armor performs its purpose. The first relates to how separate plates of armor add up, and the lesson is that separated armor plates do not add up linearly and do not provide equal resistance as one homogeneous armor plate. To simplify with an example, an armor plate of 100 mm will provide greater resistance and be harder to penetrate than two plates of 50 mm placed one on top of the other. This has to do with metallurgy, which we will cover later. The second phenomenon is the removal of the armor cap or activation of the detonator on bombs and shells. I mentioned earlier how armor-piercing shells do not detonate on contact, but delay the explosion for 0.035 seconds to ensure they detonate on the inside of the armor where they can create real damage. Anti-armor bombs function on the same principle. The point of multiple armor decks is that the fuse is activated on the first deck, which also slows the bomb, ideally enough for it to explode before it reaches the final armor plate. I mentioned another element earlier, and that is the removal of the armor cap on armor-piercing projectiles. If the outer layer of armor, for example the upper deck, can disrupt the armor cap of the projectile or induce a spin before it reaches the main armor deck or some other layer of armor, then that second layer of armor has an easier task since the projectile is no longer in optimal condition. Without the armor cap, the projectile is less penetrating and its rotation is also possible, which also reduces anti-armor performance. Finally, although bulkheads of 20 mm cannot stop any serious projectile or bomb, they can help in stopping splinters that are created after an explosion. Most of the bow and stern and the entire superstructure were lightly armored only against splinters. The exception is the armored command tower with 350 mm of armor. Interestingly, the British at this time stopped installing an armored tower on their battleships, since it turned out that captains, wherever possible, commanded from open platforms or platforms with better visibility. As you can see, evaluating how effective armor is very complex and depends on a large number of factors. As for the gun turrets, their armor is less impressive than the rest of the ship. 360 mm or 14.2 inches on the front side, 220 on the side, and 130 on the roof is not insignificant, but it is nothing special compared to, for example, American battleships, which had 457 mm or 18 inches of armor on the front side of the main battery, along with 184 mm on the roof. But it was comparable with British battleships. The Barbettes had 340 mm or 13.4 inches of armor in the upper part, above the main armor deck, and 220 mm or 8.7 inches in the lower part, which was also protected by the forward and aft armor of the Citadel. Now it is time for me to try to explain what Bismarck's armor looked like in a 3D model in the game World of Warships. So, here in the game World of Warships, we can clearly see the different layers of armor and the better and not so well protected parts of a warship. The green parts are the unarmored parts of usually the superstructure, the yellow is mediumly armored parts of the ship, and the dark red is the best protected parts of the ships. So if we turn off these various layers, we can see where the ship's citadel is. As you can see, it is located slightly below the waterline, and this is where all the machinery and the ammunition is stored. So this is the part that has to be protected at all costs in order to preserve the ship as a fighting unit. It is therefore heavily protected by various other layers of armor. We can see the front and the back armor of the Citadel, but we also have to keep in mind that the barbettes are immediately behind the frontal and rear part. And we have the torpedo bulkhead, which we will talk about a little bit later, and we have the main armor deck, 100 or 80 millimeters of horizontal armor. If we turn on the upper part, then we see the main armor belt, the upper armor belt, and the upper armored deck. The armor belt is the main protection of the ship. It is quite close to the waterline and slightly below it, and therefore it prevents projectiles from entering the citadel. The upper part of the hull is less armored, but also there is no crucial machinery in the upper part, protected by the upper armor belt, which we can see right now. And the upper deck is the one which doesn't stop the projectiles but slows them down before they get to the citadel, which then fully armors and defends the ship. These frontal parts are, as I've said, are reinforced by barbettes immediately behind them. Therefore, they don't have to be as thick as the main armor belt, because what they're protecting is further protected by those barbettes. We can see the outer armor belt, and here we can see the inner main armor deck of 120 millimeters, which is at a very steep angle compared to the horizontal, which allows it to better protect the upper side, the most exposed part of the citadel. By combining these two armor plates, Bismarck is very well protected against horizontal fire. In this view, we can see the ship's barbettes, which are the armor tubes which connect armored turrets to the citadel, and ammunition hoists run through these barbettes. The armored turrets are protected by armor of various thickness. It's thickest at the front, which is usually pointed towards the enemy. It's sloped in the upper part of the turrets, where it is not as thick because it relies on the slope to increase its effective thickness. And all of this armor is combined, as we can see here. For the torpedo protection, we have the thin side plating, two layers, one with air and one with liquids, between the side plating and the inner torpedo bulkhead, which is 45 millimeters thick. And this system, especially in its middle, where it's thickest, has proven quite effective at stopping torpedoes. Here we can see the armor on the stern of the ship and the armored plate, which protects the steering gear. And we can see there is same at the bow of the ship. As we said, that's a historical thing on German ships because they lost a battle cruiser by a hit to the bow. So they wanted to prevent it so it doesn't happen if small guns fire, like those from destroyers, hit the prow of the ship. At the superstructure, only the conning tower and the rear fire control room are somewhat armored, while the rest of the superstructure is, as we can see, mostly unarmored. Anti-torpedo protection had two layers. Its total depth was 5.4 meters in the middle of the ship and 3 meters at the first and last gun turret. The depth of anti-torpedo protection was a key factor in absorbing the explosion of a torpedo, since sufficient armor to keep the explosion outside the ship was an impossible task. The protection consisted of two layers. The first layer was external and was empty, that is, full of air, and represented a reserve of buoyancy. This external layer could be filled with seawater if necessary, for example when it was needed to correct the ship due to flooding on the opposite side. Also, this space absorbed part of the energy for the torpedo explosions. The second layer was filled with liquids, that is, fuel or water for steam engines. It also served to slow down splinters created by the explosion, and helped the remaining energy of the explosion to be distributed more evenly on the ship's hull. Finally, on the inner side of these two layers was an armored bulkhead of 45 mm or 1.8 inches. This system was designed to absorb an impact of 250 kilograms of explosives, which was the standard weight of an aerial torpedo of that era. As we will see later, in that task, the system mostly accomplished its mission. The entire ship was divided into 22 watertight compartments, of which 17 were located within the citadel. Above the main armor deck, the ship was additionally divided into smaller compartments, armored with the mentioned 20 mm plate, and with 3 vertical bulkheads of 30 mm. In this way, below the main deck and above the armor deck, there were an additional 102 compartments on 2 levels. This provided additional protection from smaller projectiles and limited damage from splinters created by the explosion of heavy shells or bombs. It also provided additional protection in case of flooding, which would thus be limited to only one part of the ship. It is time to say a word or two about metallurgy as well. Namely, not every armor plate is created equal. We will not go into too much details on this issue because it is extremely complex, so I will just present a few facts. Armor plates are cast from steel whose composition is improved by adding certain metals in order to improve its properties. In the case of German armor in the Second World War, the process used is called crop-cemented armor new type. The added metals were chromium, nickel, and molybdenum. After that, an important property of armor is the method and depth to which the armor is hardened. Namely, the hardening process serves to carburize one side of the armor, heat it in a special furnace, and later cool it under great pressure in such a way to increase the carbon content on one side, which makes that side of the armor harder, but also more brittle. Perhaps the best comparison for this process is glass or a plate. They are hard until the moment they break, and then they break completely. However, in that breaking process, this layer takes away a large amount of energy from the incoming projectile. For the same reason, modern tanks use ceramics in front of other, more elastic layers. The backside remains softer, more elastic steel, which absorbs the fragments of the front brittle layer and the projectile itself, ideally without letting them into the rest of the ship. This process creates armored steel, which for the same weight provides significantly better protection than ordinary steel. The Germans hardened up to 40% of the front side of the armor, which was an average value. British armor was hardened some 30%, while American Class A armor was hardened up to as much as 55% of the armor plate depth. The positive effect of hardening was less effective the heavier the projectile was, while it was most useful in breaking up medium and lighter projectiles. Therefore, we can say that against heavy projectiles, British armor was the best, while American armor functioned best on cruisers and smaller ships, where its properties gave better performance against smaller projectiles. By its chemical composition and stated hardness, German armor was average. Japanese armor was the worst, up to 15% less effective compared to the British armor. Now, having studied Bismarck's armor so thoroughly, it's time to look at one more illustration and draw some conclusions. As we can see from the black lines on the left, horizontal hits had no chance of passing through the armor and inflicting decisive damage on Bismarck. On the left side, we see a hit that passes through the main armor belt and is stopped on the sloped armor of the main armor deck. For such a hit, we have already established that it has little chance of penetrating into the citadel. Above it, we see a black line that simulates a hit that penetrates the main armor belt, but at such an angle that the main armor deck has no problem stopping such a horizontal hit. The shell will still probably explode and inflict significant damage in the interior of the ship, but not in critical parts. A large number of smaller armored bulkheads will limit the damage that shell fragments can inflict. On the right side, in red, we see two hits that have a realistic chance of inflicting critical damage. We see a shell falling at an angle of 45 degrees, meaning it comes from the long range of 25 kilometers or more, penetrating all three deck layers and exploding in the middle of the ship, potentially inflicting catastrophic damage. If we look at the calculator, the combined effective armor of all three decks at this angle is 225 mm or 8.8 inches. A heavy projectile, even if the armor cap is removed when penetrating the first deck, will not be stopped in this scenario. This is the worst scenario for Bismarck, although it should be taken into account that at this distance it is extremely difficult to achieve a hit. This happened only twice in history, by Warspite and Scharnhorst, which we can almost consider an exception. Below it, we see a shell coming at an angle of approximately 30 degrees, thus still from a range of over 20 kilometers, passing through the upper armor belt and after that penetrating two decks. The total thickness of all armor layers that need to be penetrated is about an effective 361 mm or 14.2 inches, with the upper armor certainly removing the armor cap and initiating the fuse, so that the main deck in this scenario even has some chance of stopping the projectile. But even in that case, the damage inflicted will be large due to the internal explosion of the projectile, just outside the citadel. In a conclusion, what can all this data tell us about the question from the beginning of this chapter? Was the armor on Bismarck outdated, or is it a good solution? The answer is, as is often the case, both yes and no. Bismarck was designed for combat at short range, which for battleships means below 15 kilometers. At such range, its critical components were comparatively better protected than those on comparable battleships. At greater distances, other modern battleships were better protected, along with the fact they were all lighter than Bismarck. Therefore, it is clear that the armor on Bismarck has clear advantages and disadvantages. If tactically the battle unfolds in such a way as to exploit Bismarck's strong points, then we absolutely cannot speak of an outdated armor. The main factor of the distance at which the battle takes place is the speed of the ship, which is an aspect in which Bismarck was in a fairly favorable position. Therefore, I do not consider that the distribution of armor on Bismarck was necessarily bad, although I do think that in some aspects it could have been better distributed. For example, the armor plates at the bow and stern served no particular purpose, and the weight could have been redistributed for strengthening the armor of the gun turrets. At the very end of this chapter, I must mention that when we talk about armor and zones of immunity, for most new ships this refers to ranges above 15 or generally 20 kilometers, depending on the weapons being fired at them. In the era of the Second World War, it was well known and acknowledged, for example by Bismarck's designer Admiral Karl Witzel, that the development of large caliber guns with armor caps had made armor that would be immune to them impractical and therefore effectively impossible. Below 20 kilometers, almost every battleship could penetrate the armor belt of any other battleship. Armor therefore helps to reduce damage or keep it outside critical zones. All battles between battleships in the Second World War, if they went to the end, to the destruction of the opponent, were mostly decided by first lucky hits that in some way disabled the opponent. This was the case with Bismarck as well, and a different distribution of armor probably would not have helped it. Strategically speaking, Bismarck could have been designed differently so as to obtain the same or better combat characteristics with less weight, except at short range where it was truly well armored. Despite this, in real conditions of World War II, Bismarck was capable of accepting combat against almost any opponent with a fair chance to win the engagement. It's time to talk about Bismarck's propulsion: propellers, rudders, bow, stability, aircraft, and living conditions of the crew. Sounds interesting? Let's get started. When Bismarck was designed, there were three possible types of propulsion, and Germany had experience with all three. The first was diesel propulsion, as on the Deutschland-class heavy cruisers. Germany was the only naval power that had experience with diesel engines on capital ships, but even for them, the size of the new ships proved too much of a challenge. Diesel engines offered the best efficiency and therefore the best range, which was important for operations deep in the Atlantic. However, diesel engines of this size had not been built before, and it was known from the start that they were also the heaviest option. Since weight was a problem from the very beginning due to the required armament, armor, and speed, this option was quickly abandoned. The second option was turbo-electric propulsion. In this configuration, steam engines are connected to huge generators, which create electricity for electric motors that drive the propellers. The Americans, at the end of the First World War, were building battleships and later Lexington-class aircraft carriers with such propulsion. And Germany had positive experience with this propulsion on large ocean liners. The fact that the propellers did not have mechanical connection with the turbines eliminated large shafts, which reduced noise and vibrations and simplified the internal arrangement. In this case, the position of the boilers and generators was not conditioned by the position of the reduction gear, which does not exist in this system, so it was possible to construct smaller and better protected compartments for propulsion. It is much easier to run one electrical cable through the ship than a shaft of about 100 meters and several dozen tons that rotates 4 times per second. Another advantage is that it was easy to turn the propellers in the other direction, since it was only necessary to change the polarity of the electric motor, which made maneuvering easier. Reverse travel with steam engines is not simple because it is necessary to disconnect the main turbine and redirect steam to a special, usually smaller turbine in order to obtain the rotation of the propellers in the opposite direction. However, although the problem was less pronounced than with diesel engines, electric motors were heavy. Here we even have a figure. Compared to classic turbines, Turboelectric propulsion was 600 tons heavier for the same power. The huge amount of copper required for electric motors was not only heavy, but also represented a strategic problem, since this was a metal that Germany exclusively imported. This same propulsion was considered for their tanks later in the war, and for reasons of scarcity of raw materials, it was abandoned. The company Siemens withdrew from the competition because it believed it would not be able to construct motors that could be switched from full forward to full reverse propulsion in just 20 seconds, which was the Navy's requirement. They believed that the electric motors would overheat in such conditions. Therefore, immediately before the start of construction, it was decided that the propulsion would be the classic turbine steam engine, although with the modern technology in the form of high-pressure boilers. This propulsion offered the greatest power for the least weight, and was also robust, that is, more resistant to damage caused by vibrations due to possible hits. Efficiency, as in the fuel consumption, was the lowest, but for a given weight, the power and thus the speed that could be obtained was the greatest. It is difficult to say which characteristic is more important for a ship intended for attacking convoys, range or speed. Such a ship must be able to cruise for a long time, but also be fast enough either to catch its prey or to be able to quickly withdraw in case of a heavily defended convoy or organized pursuit. The Germans understood that the latter is a prerequisite for survival, and range would be ensured by tankers that would be positioned in advance at refueling points at sea. The total range, due to the size of the ship, was nevertheless considerable, since on internal supplies it could travel about 17,100 kilometers at a speed of 15 knots, or 15,000 kilometers at cruising speed of 19 knots, although of course this dropped significantly when higher speed was used. Specifically, at a speed of 28 knots, Bismarck could travel less than half the distance, about 7,200 kilometers. American North Carolina-class battleships had enormous range of 24,000 kilometers at 15 knots, and therefore often served as tankers for their escorting destroyers. At the other end of the spectrum are the Littorio-class battleships. For operations in the Mediterranean, they did not need more than 6,000 kilometers of range at 20 knots. The engine room in Bismarck had 12 boilers with very high operating temperatures of 465 degrees Celsius and pressure of 58 kilograms per square centimeter. These are very high figures, the highest in the Second World War, which required the latest materials and technologies to be reliable in practice. Judging by the experience of the battlecruisers Scharnhorst and Gneisenau, German engines were not as reliable as the Navy command had hoped. Bismarck's career was too short for this to come to the fore. Originally, it was intended that the temperatures in the boilers be 540 degrees, which would ensure greater efficiency, but shortages of necessary materials, rare metals and alloys that can withstand such operating stress caused problems, and the operating temperature had to be reduced. This reduced the efficiency of the engines. In normal cruising, 2 boilers per shaft were used, but all 4 were fired when higher speed was needed. The boilers heated up quickly and provided propulsion 20 minutes after cold start. Steam from the boilers drove 3 turbines, which drove 3 shafts and 3 propellers. The turbine design is considered the weaker part of the overall design, since they were slow and connected to only 1 reduction gear, while other navies had 2 reduction gears between turbines and shafts. 2 reduction gears would enable higher turbine rotation speeds, which would reduce the number of boilers and fuel consumption. Thus, Bismarck consumed 325 grams of fuel per 1 horsepower per hour, which is worse than, for example, American ships, which consumed 305 grams under the same conditions. All of this was sufficient for about 138,000 horsepower. In steam engines, it was always possible to obtain greater power by increasing temperature beyond specifications. Thus, Bismarck achieved power of 150,000 in trials and Tirpitz 163,000 horsepower. Tirpitz's engine room was identical to Bismarck's except for a different turbine manufacturer and the addition of a special cruising turbine, which did not affect maximum power. The difference is, probably, that in Tirpitz they decided to take more risk during trials in order to find out what the real maximum of the propulsion system was. As for electricity, the ship could produce 8 megawatts of electricity. In normal operations, it needed 4 megawatts, and in combat conditions, 6. Half of this capacity was created through the main engine room, and the other half through diesel generators, in 4 separate spaces throughout the ship. This was supposed to help ensure that in case of damage to one part of the ship, electricity would continue to be produced. There was also a reserve of 2 megawatts via diesel generators if the main engine was damaged. Now we come to an important item. Bismarck was built with 3 shafts and 3 propellers, while other navies had used 4 propellers. Why? Didn't the Germans know that with 4 propellers it is easier to steer without rudders? They did, but again, they had their reasons why they chose this system. 3 propellers mean 3 shafts, which are less heavy than 4, so in that respect, this system is more efficient. Also, 3 shafts divided the ship into 3 longitudinal departments, which in case of flooding on one side of the ship was considered more stable than 2 compartments, which is standard on systems with 4 shafts. One important problem of the system with 3 propellers is a weaker stern. The space needed for the central propeller meant that the keel breaks off earlier and the stern rises without its support. German capital ships were therefore more vulnerable to torpedo hits in the stern than average. This can be seen, for example, on the stern of the cruiser Prince Eugen, which almost fell off after a torpedo hit from the submarine Trident in 1942. In the end, they had to saw it off and weld a new one in its place. Of course, there were similar cases with, for example, American cruisers, which used to lose their entire bow, but this was due to hits by much larger Japanese torpedoes called Long Lance, which had a warhead of 490 kilograms of explosives, much more than the standard 350 kilograms on British submarines. The bow and stern are always a vulnerable part of large ships due to the narrowing of the hull, which meant less anti-torpedo protection. But the German system with 3 propellers made the sterns of such ships particularly vulnerable. Before the final analysis of this system, I must also mention the rudders. Bismarck had 2 of them, which was standard for this era. One rudder was considered too vulnerable, so the second was there, both for better performance and for better protection through redundancy. But the problem of the narrow and high stern meant that the only possible place for the rudders was relatively close to the center, which meant they were very close together. Thus, in reality, that redundancy did not exist, since one torpedo hit could and did disable both rudders. Bismarck's rudders were relatively large compared to the rest of the ship, and this ensured excellent maneuvering characteristics at high speed. Propellers and rudders have always been vulnerable parts of the ships, and a real way to protect them has never really been found. External guards, or skegs, would help, but created hydrodynamic resistance which negatively affected speed, and also made the rudders less effective. Japanese designers of Yamato tried to solve this problem through an auxiliary rudder in front of the main one. Although a good idea in theory, in practice, this system proved inadequate. The best solution was probably one by the Littoria class. That ship had 4 propellers, but also 3 rudders, so that in case of damage to any rudder, the other 2 were sufficient to direct the ship where needed. This proved crucial for the survival of Vittorio Veneto, which was hit by a torpedo in the stern in the Battle of Matapan, but unlike Bismarck, withstood that hit better and returned to port under its own power. Systems with 4 propellers have the already mentioned advantage in turning without rudders, combining reverse and forward travel on opposite sides. But with such large and long ships with enormous lateral hydrodynamic forces, navigation using only propellers was a huge problem for both systems. The system with 4 propellers also had one additional vulnerability, and that is that the outer shafts passed closer to the edge of the ship than the system with 3 propellers. This meant they were more vulnerable to the damage over a wider area. This was the direct reason for the loss of the battleship Prince of Wales. A Japanese torpedo knocked the left outer shaft out of its bearing, which continued to rotate at full speed for some time, and caused enormous damage inside the ship, which lost the ability to maneuver after that, and was soon sunk. Therefore, the system with 4 propellers also has its problems, and it's not automatically better than the system with 3. In the end, Bismarck was not lost because of its propeller system, but because both its rudders were jammed. In such a situation, any battleship, except perhaps Littorio, would be in huge trouble, and a different propeller system probably would not have succeeded in compensating for the jammed rudders. In case of a hit like the one on Bismarck, all battleships of that time would probably have lost the ability to maintain course. Now we move from the rear to the front part of the ship. You may not have known, but Bismarck underwent plastic surgery on its nose shortly after launching. Namely, on Scharnhorst, a problem was discovered with excessive flooding of the ship's bow, which seriously interfered with the forward turret in combat operations. This was fixed in the shipyard, where they were fitted with a new raised, so-called clipper or Atlantic bow. This is clearly visible in the pictures, and that plastic surgery was done in January 1940. Tirpitz was built from the start with a new bow, which largely solved the earlier problems. Bismarck was designed with high metacentric height, which meant it was very stable. The placement of so much armor low on the hull and the thin upper armor deck ensured that stability. Both during maneuvers and during storms, their stability was an advantage for gunnery, on which the rolling of the ship had very little effect. High metacentric height also had an disadvantage. The ship was very resistant to rolling until the moment when the forces became too strong and the ship would suddenly pull back to a stable state, which would disrupt aiming. British ships were built with lower metacentric height, which means they rolled more and moved in accordance with the waves and movement of the sea. But these movements were gentle and predictable, so gunners could more easily predict when the right moment for firing would be. It's time to say a few more words about the aircraft these ships carried. These were 4 Arado 196 aircraft, for which there was a hangar located in the middle of the ship. The aircraft served for reconnaissance in good weather, and potentially for observation of long-range fire. The aircraft were launched by a double-sided catapult running on compressed air. It was 32 meters long, located in front of the hangar. Airplanes were lifted from the sea using 2 cranes right next to that catapult. Hangars located in the middle were not an ideal place due to the potential for fire from fuel for these aircraft. The American Navy, after the battles of Guadalcanal, realized how big a problem this was and moved the catapults to the stern of the ship. Of course, there they were vulnerable to damage caused by the action of their own guns, from which they were protected in hangars in the middle of the ship. But this was considered a smaller problem in combat, when gunnery was most important and the survival of aircraft on deck was secondary. Now that we have finished with all the technical details are considered relevant, perhaps just a few words about how the crew lived on the ship. Over 2,000 crew members each had their own bed, and if necessary, the ship could accommodate almost twice as many. It was possible to set up hanging beds for 1,600 additional men. Spaces for the crew were mostly at the bow and stern, in front of and behind the armored citadel. The ship was like a floating city and had everything necessary for a long voyage. Thus, on the ship were infirmaries, dentists, barbers, and various workshops for any repairs at sea. The crew had at their disposal 2 canteens where they could buy cigarettes, beer, chocolate, cookies, papers, and pencil for letters, and such. According to surviving crew members, the ship could carry over 500 barrels of 50 liters of beer, and half a liter cost 30 pfennigs. It is interesting that the British gave their ship's crews a daily ration of grog, hard liquor, while American ships were completely dry, without alcohol. But the Americans had ice cream instead, which they secretly exchanged for alcohol whenever they were in contact with British ships. Food on Bismarck was served in 2 mess halls, and there was also a third only for officers. Meals were typically German: butter and jam, potatoes and dumplings, meat and sausages. All of this was kept in refrigerators at the bottom of the ship. Key rooms, such as infirmaries, were air-conditioned, and 230 fans ensured circulation of fresh air, especially in the engine room. And so, we have come to the end of today's video, and to the end of the technical part of the documentary about Bismarck. I hope you enjoyed it and learned something new. But we are only halfway there. Very soon, the series will continue with a video about the Bismarck's only operation, Operation Rheinübung. Please like and subscribe to the channel using a bell icon so that you don't miss the sequel, as well as any other videos which will come soon. I hope to see you again soon.